All right, so section 2.1 part 2 is evaluating limits. All right, so we're going to go really quickly through a lot of this. Are you ready? Really quickly. Very basic. Don't worry. All right, so the first one says the limit as x goes to a of f of x plus g of x. Basically, you can bring the limit into both pieces. So you can say it's the same as limit of f of x plus limit as x goes to a of g of x, right? Same for subtraction. Constants you can bring out. So a constant can go to the front, right, and multiplying c times f of x, equals c times the limit of x goes to a of f of x. Products, you can bring the limit in. Quotients, you can bring the limit in, as long as on the bottom you don't have zero. All right, it's easy to believe that the 5 properties above are true. So for instance, when x gets closer to a, let's say our function f is close to some m value, and g of x is close to n. So we have g of x here, f of x is here, and it gets closer to n. Do you guys know that if you add f of x and g of x, you're basically adding the y value? And since you talk about adding this y value plus this y value down here, this y value and this y value. You know, you can add different y values and get a new function. So if you add the two y values, you have n plus n. So f of x plus g of x would get closer to n plus n. Basically, you just take the limit of f of both of them and then add their limit to that. All right. So it says use the limit laws in the graphs of f and g to evaluate the following limits that they exist. So if you see the limit as x goes to -2 of f of x plus 5 times g of x, you guys see that that's going to be the limit as x goes to -2 of f of x plus, you can just pull the 5 out with 5 times something with x. Really, the limit part only has to go when you have x's. It has to go with that part. G of x. You see that? That's what we're really going to have today. So anything that has an x still has the limit with it. All right, so the limit as x goes to -2. So you just did this little worksheet on this. So as you get closer and closer to -2, what's the y value you're getting closer and closer to? 3. Plus 5 times, how about g of x? So g of x is over here. So at -2, you're closer and closer to a y value of 2. So 3 plus 10 is 13. All right, b. So we have the limit as x goes to 1 of f of x times g of x. So you can bring the limit into both pieces. You're finding the limit for the first graph, and then you're multiplying by the limit on the second graph. Does that make sense? And you can see it we have each individual. All right, so the limit as x goes to 1 of f of x, what's that going to be? 2, because you're looking at your f of x graph, so it's right there. It's at a height of 2. And then the limit as x goes to 1 of g of x, 0, exactly. So 2 times 0 is 0. No, I'm using the x value associated with the limit, like x goes to 1. All right, so limit as x goes to 3, so that's going to be the limit as x goes to 3 of f of x over the limit as x goes to 3 of g of x. Okay, so on my f of x graph, as I get closer and closer to 3, what y value am I closer and closer to? 1. And on my g graph, as I get closer and closer to 3, yes, I know 2. So the answer is 1. Yes. No, you don't have to write out this first step that I did. I'm just showing you, like, those are the limit laws that you can bring the limit into a coherent or product. See the same one. All right. So the next one, so limit as x goes to 0. So do you guys see this is going to be 2 times the limit as x goes to 0 of f of x plus 3 times the limit as x goes to 0 of g of x. So basically anything that has an x will have the limit part with it. So 2 times the limit as x goes to 0 of f of x, what's that? Yeah, what do you mean by it's hard to say? It does not exist. So if the first part did not exist, then the rest of it did not exist. So you're done. So once one of it does not exist, then the whole thing doesn't exist. Okay, so remember it does not exist because the left goes towards, it looks like 3, and the right side goes towards 1. So since they don't have the same value, it does not exist. All right, so same thing for the next one. So 2 times the limit as x goes to 5 of f of x plus 3 times the limit as x goes to 5 of g of x. So when you talk about the limit as x goes to 5 of f of x, we were at 1, 2, 3, 4, 5. That's right here. Looks like a height of, is it 4? 1, 2, 3, 4. So you have 2 times 4 plus 3 times, so x goes to, oh, I looked in the wrong one. Man, you could have got a bonus point. I caught it. You just, did you touch it? Did you touch it? Did you say it after I said it? Okay. So I'll give to Mariah. Mariah gets bonus point. All right, so we have 2 times, so she says 3. So x goes to 5. 1, 2, 3, 4, 5. So it's at 3. Plus 3 times, now this other one was 4, right? This one. So 6 plus 12, so you get 18. So 18, 3. You like when it's so fun?
That's the most fun I've had.
Well. All right. Same for other limit laws. Basically, if you have like f of x raised to the n, you can think of it as f of x times f of x times f of x n times. So you can break up all of those into separate limits. So you have the limit of f of x times itself n times. So it ends up being the limit of f of x. Yeah. Okay, so I have that right now. Okay, how about pictures? So limit as x goes to a of c. So c is just a number. So let's say my function is at a height of c. So f of x equals c. What's the limit as x goes to a? Limit as x goes to a of c is what? C. It's itself. C. All right, now the other picture is if you have the function y equals x, right? F of x equals x. That's the line with slope 1 through 0, 0. So now if I'm approaching a, what is the height? A, exactly. You can do yourself. Now that's one where you can do like a direct up, so you can do sub n. The, so since that x goes to a of x, x goes to a. All right. So same thing with these limit laws. So if you have the limit as x goes to a of x to the n, well, you can just plug in a, so it ends up being a to the n. So the x value is going to a, it's changing to a. Same thing here, this ends up being the nth root of a. And the 11th limit law falls for number 10, so if you have the nth root of f of x, sorry, nth root of f of x, it's the nth root of the limit as x goes to a of f of x. So you can bring the limit into roots as well. All right, so it says evaluate the following limits and justify each step. Okay, this is really annoying to justify each step. This is what you're going to do for number 1. You don't have to write this down. You can just watch me. It's fine. All right, so you bring the limit into the sum. So you would say, okay, I have limit as x goes to 2 of 3x squared minus limit as x goes to 2 of 2x plus limit as x goes to 2 of 8, right? You with me? Then you bring all your numbers out. So 3 limit as x goes to 2 of x squared, you with me? Minus 2 limit as x goes to 2 of x. Plus limit as x goes to 2 of 8, what's that? 8, that was from the one way. All right, and then you have limit as x goes to 2 of x squared. Well, that's the limit as x goes to 2 of x, and then squared. You with me? So it's like really annoying to write all of the steps out. I won't make you do this, don't worry. All right, so basically what's happening is if you start at your beginning, what can you do? Factor. What can you do in the original? how do you find the limit as x goes to 2 of a polynomial? What do you do? Is it ever undefined? You're not getting 0 over 0. What do? You just plug it in. Right? Does that make sense? So in the original, you just plug in 2. So you get 3 times 4 minus 2 times 2 plus 8. So 12 minus 4, so 8 plus 8 is 16. So 16. All right, you don't have to go through and do all of the limits. I just plugged in 2. Yep. There's no replacement undefined. Think about what the graph looks like. It's whatever graph you have, right? 3x squared minus 2x plus 8, so something like that. And if you plug in 2, you get a number out, right? That's all it's saying. There's never a place where it's like a piecewise function undefined. Oh, I was just shortcutting everything. Like, you would really have to write out this kind of stuff if you want to justify everything. How did I go from here to here? Is that what you're asking? That was the one where you said that was limit law 8. Limit as x goes to 2 of x is equal to 2. Yeah. I don't know, can you? Let's try it on this next one. So what if I plug in negative 2 here? So if I have negative 2, so I'm going to have limit as x goes to negative 2 of negative 2 cubed minus 8 over 6 minus 3 times negative 2. Does it work? Yeah, we get negative. I don't need the limit in front, actually. I had already plugged it in. So limit that limit. All right, so I get negative 8 minus 9 over 6 plus 6. So I get negative 17 over 12. Good? That's the answer. So you're like, well, why do we learn limits? Why is this just not f of x? And then you plug in the number. All right, some of them do give you 0 over 0. You need to use some kind of manipulation. All right, so it says, no, if we had let f of x equal 3x squared minus 2x plus 8 in example 1, you could have just computed f of 2, which was 16. In other words, you get the same answer by just substituting 2 into x. Same is true for number 2. If you just substitute in negative 2, you get the answer. This is because polynomial and rational functions, you can do that substitution. You can substitute in, except when your rational function has 0 in the denominator. It's going to have to manipulate it in some way. All right, so this is called the direct substitution property. So it says if f is polynomial or rational and a is in the domain, that means you're not getting undefined when you plug it in, then the limit as x goes to a of f of x is the same as if you just plugged in a into it. You like those? So that's always the first thing I check when I have a limit problem. I'm like, oh, can I plug in a number? If you get a number out, that's your answer. If you get undefined, that's not your answer. You gotta keep doing something. All right, so why could you not use it for something like this? Well, on this, x equals 2 isn't in the domain. Right, there's a vertical asymptote there. It's not in the domain. So you can't use the direct substitution property if you're getting a 0 on the side. I don't know, this one could factor, right? All right, so let's try number 1. So it says find the limit as x goes to negative 3 of x squared minus 9 all over x plus 3. The first thing you do is you always say, can I plug in the number? So if you plug in negative 3, what are you getting? 0 over 0. So that's bad. That's undefined. You don't know what that is. So then we're like, oh, well, is it really undefined? Can I have a limit? Let's see. So we do some kind of split. So in this case, it's going to be factoring. So you're going to have x plus 3 times x minus 3 all over x plus 3. And the x plus 3 is reduced down. So you get the limit as x goes to negative 3 of x minus 3. Now can you plug in? Yeah. So when you can plug in, then you can stop writing limit because then you just plug it in. So negative 3 minus 3. So you get negative 6. So your answer is negative 6. So 0 over 0 magically became negative 6. Yeah. What do you mean you can't just that x? Like if you got rid of this stuff? Is that what you're saying? Or this stuff? Like you went from here to here? I would show the step where you have simplified it with the word limit. All right, next step. All right, so find the limit as x goes to -3. Did you just do this one? It's the same one. Am I crazy? Oh, okay, yeah. So you don't have that, right? I just copied it again. All right, so it says if f of x is g of x when x is not equal to a, then the limit as x approaches a of f of x equals the limit as x approaches a of g of x, provided the limit is. So it's saying f of x is the same as g of x everywhere except at a. Well, if it's the same everywhere, so like let's say I have some kind of curve and that's f of x, but at a on f of x is open. And then let's say g of x is the same thing, but maybe at a it's kind of close to flip it. All right? You guys have a limit to the same thing. The limits end up being the same. Okay. So because as you're approaching a little neighborhood, it's still the same values. All right, so number one, it says find the limit as x goes to 1 of g of x, where g of x is equal to x minus 2 if x is not equal to 1. So x minus 2 is the line that goes through -2, 0, -2, and the slope of 1, so up 1, right 1, up 1, right 1. So it equals this line, except at x equals 1, it's not equal. So we're going to do an open circle there. All right, and then it's equal to 5 if x is equal to 1. So that's 1, 2, 3, 4, 5. So what would you say the limit as x goes to 1 of g of x is? -1. Does that make sense? So remember, limit is the y value you're getting closer and closer to these two. So if you were doing like a little table of values, as you get closer and closer to 1. So 1.01, 1.001, 1.00001. You're getting closer and closer to -1. How did I get that? Oh, because I have y equals x minus 2. So it has a y-intercept of -2 and a slope of 1. All right, so you've seen kind of the factoring trick. There's another trick, which is called the FOIL trick. All right, so if I see the limit as h goes to 0 of 2 minus h squared minus 4 all over h. All right, right now if you plug in h is 0, do you see you get 0 over 0? So that's bad. So we're going to multiply out. So instead of having 2 minus h squared, I'm going to do 2 minus h times itself. So I'm going to get 4 minus 4h plus h squared minus 4 all over h. So I multiplied it out. Now what happens? 4 minus 4 goes away, so I get -4h plus h squared all over h. Can you eliminate the 0 over 0? Yeah, so you can divide that h on the top and bottom, so you get -4 plus h. So what's your answer? -1. You like this little trick? I would like to. All right. Next up. All right, there's factoring trick. So we've done it with like x squared minus 4, but x minus 2. Same thing here. It would equal -4. Because you're left. Because h goes to 0. So if you plug in 0, you get -4. Yeah, so basically keep your limit until you're able to plug in. Okay. So this one's a factoring trick. So I have the limit as x goes to 4. So right now I have 0 over 0. All right, so I'm going to factor the top. I'm guessing that there's probably an x minus 4. So what else do you need in the other parentheses? X minus 2. Right, the x minus 4 is reduced out. So you get the limit as x goes to 4 of x minus 2. Are you able to plug in now? Yeah. So negative, or if you plug in 4, you get 4 minus 2, so you get 2. Okay, number 4. See how much you remember from algebra 2. This is the difference of two squares. Or not squares, difference of two cubes, right? So you have x cubed minus 2 cubed. Right? X cubed minus 8 is x cubed minus 2 cubed. Didn't I do this on the summer packet? Remember the pattern? So the binomial, so the two-term one, drop the cubes. So you get x minus 2. All right, the next one. Square the first item that you had. So take that x and you square it, so x squared. Take the 2 and square it, so you get 4. Multiply the 2 together and get 2x. And your signs are same, opposite, always positive. So, and I said same, different, plus. There we go. So, so the same, opposite, always positive. So it's going to be negative, plus, plus. All right, so that's how that one factors. So it's going to be the limit as x goes to 2 of x minus 2 times x squared plus 2x plus 4 over x minus 2. The x minus 2's cancel. So now you've eliminated the part that was missing undefined. So you're going to get the limit as x goes to 2 of x squared plus 2x plus 4, which is 4 plus 4 plus 4. Right, 2 squared plus 2 times 2 plus 4. All right, next step. A couple more tricks. I call this the rationalizing trick. All right, so the rationalizing trick. So you guys remember if you had 1 over the square root of 2, how do you rationalize that? Multiply by root 2 over root 2. Okay. What if I had 1 over root 2 plus 3? Yep, you multiply by root 2 minus 3 over root 2 minus 3. Do you guys remember that? It's called the conjugate. Okay, so that's what we're going to do on these. Now, it's not necessarily in the denominator. Like, you could rationalize the numerator as well. Okay, so the key is if you see a square root in the problem, and when you're plugging in the value, so if I plug in 0, do you guys see how you're getting 0 over 0? All right, so that's when you're going to use this trick. You see a square root in the problem, try this trick. So what I'm going to multiply by is the conjugate of the top. So I'm going to multiply by the square root of t squared plus 9, and then I'm going to have plus 3. So I'm going to multiply on the top and the bottom. Okay, so that's going to be the limit as t goes to 0. So when you multiply the top together with the conjugate, you have the square root of t squared plus 9 times itself. So what do you get there? T squared plus 9. And then you have your outer is 3 times the square root of t squared plus 9. And your inner is negative 3 times the square root of t squared plus 9. And your last is negative 9. So that's why we multiply by the conjugate, because these now go away, right? Gone. So we have plus 1 minus. Now the bottom, always leave it in its factored form. So write yourself a little note. Leave factored. Because if you try to bring in that t squared, it's going to be on that. So leave factored. All right, so I'm going to have the limit as t goes to 0 of t squared plus 9 minus 9 So you guys see that's just t squared? Where is t squared? All over t squared times the square root of t squared plus 9 under root plus 3. You see I told you to leave it after? Yeah. This is eliminating the 0 over 0 thing because now those t squares are gone. Nope. Yeah, don't keep repeating the process. That would just be annoying because you'll just keep bouncing back between the two. So don't rationalize again. So you're going to have 1 over the square root of t squared plus 9 plus 3. Is it okay to plug in 0? Yeah, now it's okay. So now you get 1 over the square root of 9 plus 3, so you get 1 over 6. So your answer is 1/6. It's all super smart on these tricks. But, oh, I can do any limit problem. You know all of the tricks. All right, so you guys try number 6. So try to rationalize. So multiply by the conjugate of the numerator. Keep it in its factor form and hope that it cancels. So it's all about a 1/8. So let's see. So you multiplied by the conjugate. So x plus 7 plus 4, square root of x plus 7 plus 4. So you get the limit as x goes to 9. You'll have x plus 7. The outer and inner terms will cancel. That's how we designed it, right? So then you're going to have minus 16. Don't write minus 4. Some of you guys do that, right? Minus 4. 4 times 4 is 16. So the square root of x plus 7 plus 4. Is that what you did, Thomas? And you're like, oh. Yeah, common error, I feel. Oh, and I forgot something in my okay. All right, so that means that I'm going to have x minus 9 on top. I have x minus 9 on bottom. And you have the square root of x plus 7 plus 4. So those cancel. So you get the limit as x goes to 9 of 1 over the square root of x plus 7 plus 4. So when you plug in 9, you get the square root of 16. So 4 plus 4, so 1 over 8. We'll end there.